Let's talk about sound. Part 2. Frequency domain representation of sound. Greetings. From this time, I would like to talk about the representation of sound in the frequency domain. So far, we have talked with you about waveform. To briefly summarize, waveform is the change in amplitude over time. However, this picture only shows the change in the amplitude of the sound, and it is difficult to know other information such as tone or pitch. When we want to see those information in more detail, we look at this picture. But, what is this picture? How can we draw this picture and how should we interpret it? What is the difference between these two pictures? Looking at this picture, can you guess what each sound sounds like? Let's think about it for a moment and listen together.
The waveform is the representation of change in amplitude over time of sound.
In order to tell this story, we need to go to the fourth dimension, through the looking glass for a moment. First, let's talk about spectrum. But before we talk about spectrum, let me tell you something a bit more difficult. This is the theory of a very famous researcher named Fourier. A steady-state wave is composed of a series of sinusoidal components whose frequencies are those of the fundamental and its harmonics, each component having the proper amplitude and phase. What on earth does it mean? Let me omit some of the details and put it simply. Any periodic signal can be expressed as a sum of sinusoidal functions at different frequencies, amplitudes, and phases. For example, by combining the three signals below, you can create a periodic signal like the one on the right. In this way, you can simply understand that all signals with periodicity can be created by the sum of sine waves. Of course, sine waves can have different amplitudes and frequencies. Let me show you a few more examples of signal synthesis. The signals on the left are a sequence of signals with specific rules. And the very first signal has the lowest frequency. Each signal has its own amplitude and frequency. If signals with these rules are theoretically combined infinitely, a square wave like the one on the right is created. Let's listen to the sound of a square wave with 440 Hz. These are signals with different rules this time. Theoretically, if you combine these signals infinitely, you get a triangle wave like the one on the right. Let's listen to a triangle wave signal with 440 Hz. This time, it is a list of signals with different rules. As in the previous examples, if the signals on the left are theoretically combined infinitely, the result is a sawtooth wave on the right. Let's listen to a sawtooth signal with 440 Hz. Let's take a closer look at the signals that make up this sawtooth wave. When I showed you the synthesized signals earlier, I said that each signal that makes up the synthesized signal has different amplitude and frequency components. If you look closely at the signals below, you can see that the period gets shorter as you go to the first, second, and third elements. If we talk about this in terms of frequency, the frequency of each element increases by an integer multiple of the lowest frequency. The lowest frequency that forms a signal is called the fundamental frequency, and frequency components that are constant integer multiples of the fundamental frequency are called harmonics. And as you can see, each harmonic has its own amplitude. This time, let's look at another example. The signals that make up a triangle wave are as follows. As before, it consists of fundamental frequencies and harmonics, with their own amplitude, but there are a few differences. First of all, you can see that the harmonic signals are made up of odd multiples of the fundamental frequency. Another difference is that the starting point of each sine signal is different. This starting points of the sine signal is called the phase. To summarize, all signals with periodicity are made up of a signal with a specific frequency, the fundamental frequency, and a signal with a multiple of that frequency, the harmonics. These harmonic signals can each have their own amplitude, frequency, and phase. This is Fourier theory explained simply. So how can we know what frequency components a specific signal consists of? And how can I represent it? For this we need the Fourier transform and the spectrum. By using the mathematical transformation method devised by Fourier, you can find out which frequency components are included in a specific signal and how much. Let's think of the signals shown in the picture below as fundamental frequency signals and their harmonics. If you add these signals on the time axis, you will get the waveform we are looking at. And if you perform Fourier transform on the frequency axis, you can see the frequency spectrum. To explain by just looking at this picture, I think it would be good to understand that we can see waveform and spectrum respectively depending on the perspective from which we look at the signal. Let's look at an example of Fourier transform. If you perform Fourier transform on the periodic signal below, you can see the frequency spectrum as shown on the right. The x-axis is the frequency component, and the y-axis represents the magnitude of the sine wave with that frequency component. At this time, we sometimes use a technique called fast Fourier transform, or FFT for short. You can think of this as an algorithm that improves Fourier transform more efficiently. The signal we are dealing with is a sampled signal, as discussed in the previous section. This is because computers cannot handle analog signals with continuous values. There are characteristics that appear when the Fourier transform is applied to a sampled signal. That is, the frequency spectrum of a sampled signal can only represent the frequency components of that signal up to half the sampling rate of the original signal. If we think back to the Nyquist sampling theory we learned last time, it said that to fully recover the original signal, we need to sample twice as large as the original signal. In other words, a sampled signal can only express frequency components up to half of its sampling rate. Therefore, the frequency spectrum, which represents information about the frequency components of the original signal, can only express frequency components up to half the sampling frequency of the target signal. Let's look at an example of a frequency spectrum using the synthesized signals seen earlier. I told you that the components that make up the square wave are the left signals. In other words, if you combine signals with these rules infinitely, you get an ideal square wave. And if you perform Fourier transform on this square wave, you can get the spectrum as below. In this spectrum, each peak can be seen as indicating how much of the component with each frequency is included. The first peak is the fundamental frequency, expressed as f0, followed by harmonics, the second as f1, and the third as f2, etc. The case of a sawtooth wave is as follows. Different harmonics appear than square waves. For triangle waves, these go like this. This time again, it shows different harmonics than the previous two signals. Let's compare once again the square wave and triangle wave we saw earlier. What they have in common is that harmonics only appear at frequencies that are odd multiples of the fundamental frequency. However, because the relative amplitude of each harmonic component is different, it produces a completely different sound. Here, we can see that both each frequency of the harmonic content and its amplitude have a significant effect on the timbre. So far, we have talked about the frequency aspect of periodic signals with specific frequencies. However, the sounds we hear do not always have the same frequency like the triangle and square waves we have heard so far. In other words, the frequency content of these signals can be changed over time. All sound signals we hear are flows of signals with such periodicity that change very, very quickly. So how can we see frequency components that change over time?